What if the particles that make up you, me, and the entire universe were never real to begin with? From quantum ghosts to vanishing matter and the illusion of substance itself, this is the story of what reality is really made of, and why everything you know might be built on nothing. There's something strangely comforting about the word particle. It sounds solid, precise, final. A particle is supposed to be the smallest possible thing, the last indivisible grain of reality. Not a cloud, not a probability, a particle. The very word suggests that we've arrived at the bedrock of existence. But what if that word, this neat little concept, has been lying to us? For centuries, scientists have chipped away at matter, peeling it back like an onion. From rocks to minerals, from elements to atoms, from atoms to subatomic particles. And just when it seemed like we'd reached the end, we fell straight through the floor. Because the closer we look, the more everything unravels. In classical physics, particles were clean. They had position, momentum, Massachusetts. They moved through space like marbles on a table. But in the quantum world, none of those ideas hold steady. A particle can be in multiple places at once. It can pass through barriers it shouldn't. It can vanish, interfere with itself, or become entangled with something halfway across the universe. And perhaps strangest of all, it might not be a thing at all, but a temporary ripple in an invisible field, a ghost of probability that disappears the moment you try to pin it down. We still call them particles. It's a useful word. But the truth beneath it is far stranger and far less certain than most people realize. This is a story about electrons that aren't really there, about photons that behave like waves until you look at them, about quarks that have never existed outside of theory and interactions that seem to break the rules of causality. This is a story about science's most familiar building blocks and why they might not be real in the way we think. Because if particles aren't real, then neither are atoms, neither is matter, neither are you. And the answers, if they exist at all, lie somewhere deep inside the quantum void. There's a moment, usually sometime in school, when we're first told what we're made of. The teacher holds up a model of an atom, plastic balls on stiff wires like planets orbiting a miniature sun, and tells us that everything, from the desk in front of us to the stars overhead, is made of these tiny solid spheres called particles. Tiny units of matter. Neat, precise, self-contained. The idea sticks. It's comforting in a way, this notion that there are fundamental building blocks, little marbles that click together to make the universe. We're told that inside every atom are protons and neutrons clumped tightly in the center, with electrons orbiting around them like planets. We picture electrons as miniature billiard balls whirling in circles. This is the world as many people understand it. The world of the Bohr model, simple, elegant, and wildly wrong. The Bohr atom was a breakthrough in its time. It introduced the concept of quantized energy levels and explained the spectral lines of hydrogen with surprising accuracy. But it was never the whole picture. Even Niels Bohr knew that. What it offered was a scaffolding, an in-between model to bridge the chasm between classical physics and something stranger, deeper, more unnerving. Because here's the uncomfortable truth. Particles, as most of us imagine them, don't really exist. Electrons don't orbit the nucleus like tiny moons. In fact, they don't really orbit at all. They exist in clouds of probability, smeared out over space, described not by clear positions or paths, but by abstract mathematical functions called wave functions. We don't know exactly where an electron is. We can't. We can only calculate the odds of finding it at a particular location, at a particular moment, and hope we're close. The same applies to the proton and neutron. They're not indivisible chunks of matter, but complex storms of energy made up of even smaller constituents, quarks, bound together by an invisible, unrelenting force. And even quarks, as we'll see later, may not be particles in any meaningful standalone sense. They've never been observed directly. They can't be isolated. The deeper you go, the more things dissolve into uncertainty. But before we get there, let's go back to those early models, the ones that shape how we first think about matter. Take the classical idea of a particle, a small object with mass, volume, position, and momentum, something you could, in theory, hold in your hand if you were small enough. This view made sense when scientists studied gases in sealed boxes or electrons shooting through cathode ray tubes. They seem to behave like tiny bullets, bouncing, scattering, accelerating. Early experiments, like J.J. Thomson's work with electrons, suggested these were clearly particles. They moved in straight lines. They had charge. They had mass. You could count them. Even Einstein's work on the photoelectric effect seemed to reinforce this view. He proposed that light, long thought to be a wave, also came in discrete packets of energy called photons. These photons could knock electrons loose from metal surfaces in clean quantized bursts. That sounds like particle behavior, doesn't it? But right from the start there were problems. Photons also diffracted and interfered, like waves. Electrons, when fired one at a time through a pair of slits, produced interference patterns, again like waves. Sometimes they behaved like particles, sometimes like waves. It depended on how you looked at them. This dual nature, wave and particle both and neither, is at the heart of quantum mechanics. But to the average person, the classical picture sticks. Even some scientists speak in terms of particles because it's intuitive, it's convenient, it's the language our brains are built to understand. We see the world in objects, not in wave functions. And yet, when we probe deeper, the old language breaks down. Because what is a particle, really? Is it just something with mass and charge? Is it something we can observe directly? Something we can isolate, define, label? In the quantum world, the answers get blurry. An electron doesn't have a defined position until you measure it. Until then, it exists as a spread-out wave of possibilities. A photon doesn't travel from point A to point B in a clean arc. It exists in a superposition of all possible paths and interferes with itself. A quark can't be pried out of a proton and examined on its own. It exists only within the context of other quarks, held in a web of energy so strong that pulling one loose creates more particles in the process. Even the act of observation collapses possibilities into a single outcome. What you choose to measure affects what the particle seems to be. You don't just look at the universe, you participate in it. And so, we're left with a strange realization. The term particle may be nothing more than a linguistic holdover from an older, more naive physics, a placeholder, a useful fiction. We still use the word because we need something to describe the tiny events and interactions we can detect, something to label the sudden flashes on a detector screen. But what those flashes represent is far less certain. They may not be things at all. They may be events, transitions, manifestations of energy fields collapsing into localized interactions, only to dissolve again into uncertainty. If that sounds abstract, it is, but this is where physics has brought us, not to a world of little spheres bouncing in space, but to a reality where nothing is truly solid, where everything is interconnected, and where the very idea of a particle may be just a convenient illusion. In the next chapter, we'll dive into one of the most famous experiments in all of science, one that shatters the classical image of particles and forces us to confront the true weirdness of the quantum world. It's a simple experiment, but its implications are anything but, because if the particle is already a lie, the way it behaves when no one is watching may be even stranger. Before quantum mechanics took hold, light already had something of an identity crisis. Was it a wave, a particle, or something entirely different? The debate began centuries ago, long before anyone had a word like photon in their vocabulary. In the late 1600s, Isaac Newton argued that light must be made of particles, what he called corpuscles. He imagined these tiny, massless projectiles traveling in straight lines, bouncing off mirrors and bending through lenses. It fit neatly with his laws of motion and his view of a clockwork universe. Around the same time, however, Christian Huygens proposed something much stranger, that light was a wave, rippling through an invisible medium, much like sound through air or waves through water. The arguments raged on. Newton's prestige carried weight, but over time Huygens' model gained ground, especially after Thomas Young's famous double-slit experiment in the early 1800s. In it, beams of light were shone through two narrow slits onto a screen. If light were made of particles, you'd expect to see two bright bands where the light passed through each slit. But that's not what happened. Instead, the screen lit up with a series of alternating bright and dark bands, an interference pattern. That's what waves do. They combine, amplify, and cancel each other out. By the late 19th century, James Clerk Maxwell had unified electricity and magnetism into a single theory, electromagnetism, describing light as a self-propagating wave of electric and magnetic fields. The wave theory had won, at least it seemed to have. Then came the photoelectric effect. It was simple. Shine ultraviolet light on a metal plate, and electrons are ejected. But the results were baffling. If light were truly a wave, then increasing the light's intensity, making the wave stronger, should knock out more electrons. Yet it didn't. Only light above a certain frequency, no matter how weak, could eject electrons. And the higher the frequency, the more energy each electron carried. In 1905, a young patent clerk named Albert Einstein proposed a bold solution. Maybe light came in discrete packets, quanta, each carrying a fixed amount of energy based on its frequency. He called these quanta photons. This wasn't just theoretical sleight of hand. It explained the results perfectly. Bright but low-frequency light had lots of photons, but none energetic enough to knock an electron free. Dim, high-frequency light had fewer photons, but each one packed a punch. Einstein's idea, which earned him a Nobel Prize, forced physicists to accept a stunning contradiction. Light behaved like a wave and like a particle, depending on how you interacted with it. That was the beginning of wave-particle duality, and it didn't stop with light. Inspired by Einstein's success, in 1924, a French aristocrat turned physicist named Louis de Broglie flipped the idea on its head. If light could be both wave and particle, then maybe particles like electrons also had wave properties. He proposed that every particle had a wavelength, given by his now famous equation, lambda equals h over p, where lambda is wavelength, h is Planck's constant, and p is momentum. At first it sounded like science fiction, but within a few years, Clinton Davison and Lester Germer at Bell Labs confirmed it. They fired electrons at a crystal of nickel and observed a diffraction pattern, exactly the kind of interference you'd expect from waves. This was a seismic moment in physics. It wasn't just light. Matter itself had wave-like properties. The line between waves and particles was blurring into nothing. Over time, experiment after experiment confirmed this bizarre duality. Electrons, neutrons, even whole atoms and molecules showed wave-like interference patterns under the right conditions. In 1999, physicists even performed a double-slit experiment using C60 fullerenes, molecules made of 60 carbon atoms shaped like tiny soccer balls. These aren't small, they're hundreds of times more massive than a proton. And yet they produced wave interference patterns. That's not supposed to happen in a classical universe. And yet, it does. So what does this all mean? It means that the idea of a particle moving through space like a little bullet is, at best, incomplete, and at worst, misleading. Quantum entities like electrons and photons do not have fixed identities. They do not behave as particles or waves. They behave as quantum objects, described by a wave function that evolves over time and collapses upon measurement. What we observe depends on what we choose to measure. And here's the strange part. This isn't just about metaphors. These are measurable, repeatable outcomes. The double-slit experiment, in its many forms, has been performed countless times over more than a century. Its results are not in question. The interference patterns are real. The collapses are real. The paradox is real. In 2012, researchers at the University of Vienna even recorded individual C60 molecules passing through a double slit in real time, showing the interference pattern gradually building up one molecule at a time. Each molecule, fired individually, had no knowledge of the others, and yet, over time, they formed a pattern that only a wave could explain. So what passed through the slits? Was it a particle, a wave, or something that defies both categories? Some physicists have suggested that the particle doesn't exist between measurements at all, that it's not just unknown, but literally undefined. The wave function doesn't describe a blurry particle. It describes a system of probabilities, a landscape of outcomes that only crystallize into a single point when observed. Until then, it's as if the particle exists everywhere and nowhere, all at once. This is why Richard Feynman, one of the 20th century's greatest physicists, once said that the double-slit experiment contains the only mystery of quantum mechanics. Because it doesn't just contradict our understanding of particles, it contradicts our understanding of reality. We often talk about particles like they're tiny, self-contained units, little spheres with mass and charge. But the more closely we examine them, the more that image falls apart. We find wave functions, we find fields, we find probabilities. What we don't find is a particle in the classical sense. And yet, somehow, these ghostly, shape-shifting entities still build the world around us. Your screen, your skin, the stars overhead. All of it is made from things that are and are not particles. It's not just counterintuitive, it's deeply unsettling. Because if even light and matter don't behave the way we expect, then the line between what is real and what is measured begins to blur. And the closer we look, the harder it becomes to tell where reality ends and the illusion begins. It's been called the most beautiful experiment in physics, also the most disturbing. The double-slit experiment is deceptively simple. 2 slits, a beam of particles, and a screen. High school physics teachers demonstrate it with lasers. Undergraduate labs repeat it with electrons. Yet, its implications have shaken the foundations of reality for more than 100 years. Because the moment you understand what this experiment is really saying, you never look at particles the same way again. Imagine you're firing a stream of tiny bullets, say marbles, at a wall with 2 narrow gaps in it. Behind that wall is a screen that catches anything that passes through. If the marbles are truly particles, you'd expect them to go through one slit or the other and land behind it. Over time, the screen will show 2 distinct bands where the marbles hit. It's straightforward, it's classical. Now imagine you fire waves instead, ripples on a pond, or light. Each wave spreads out as it travels, passing through both slits simultaneously. When the 2 waves overlap, they interfere with one another. In some places, the crests amplify each other. In others, they cancel out completely. This interference pattern appears as a series of alternating bright and dark bands on the screen. It's beautiful, predictable, and profoundly different from the 2-band result of particles. Here's where it gets strange. Now try firing electrons, not waves, not beams. Individual electrons, one at a time, spaced far enough apart that they can't possibly interfere with each other. At first, the screen looks random, dots appearing in scattered locations. But as more electrons accumulate, something incredible emerges. The interference pattern reappears. The same pattern as if a wave had passed through both slits and interfered with itself. This is the moment that derails everything we thought we knew. Because you are firing electrons one at a time, there's no other electron for them to bounce off of. There is no wave to interfere with. And yet, somehow, each electron appears to be passing through both slits simultaneously, interfering with itself, as if it were a wave. So what's going on? According to quantum mechanics, each electron is described by a wave function, a mathematical expression of all its possible positions and paths. Until you make a measurement, that wave function evolves, spreading out in space, going through both slits. The interference pattern is a map of probabilities, not certainties. When the electron hits the screen, the wave function collapses and it materializes as a single localized point. But now comes the real twist. Put a detector next to one of the slits. Nothing fancy, just a device that tells you which slit each electron passes through, that's all. You're not touching the electrons, you're not changing their direction, you're just watching. The moment you do that, the interference pattern disappears. It's gone. What you see instead is two clumps, exactly what you'd expect from particles going through one slit or the other. Just like marbles, just like the classical world. This isn't just spooky, it's paradigm breaking. The very act of observation changes the outcome. By choosing to measure which slit the electron goes through, you've eliminated the wave-like behavior. You've collapsed the superposition prematurely. The particle now behaves like, well, a particle. But remove the detector and the interference returns. This isn't a one-off. This has been replicated with photons, electrons, neutrons, even entire atoms and molecules. The result is always the same. Observe the path, and the wave vanishes. Don't observe, and the interference returns. Feynman once said that this experiment encapsulates the entire mystery of quantum mechanics. He wasn't exaggerating, because it forces us to ask, what is the role of the observer? Does the electron somehow know it's being watched? Is reality, at its deepest level, dependent on measurement? In 2014, a study published in Nature Communications went even further. It showed that wave-particle duality is mathematically equivalent to the Heisenberg Uncertainty Principle. In other words, the uncertainty about where a particle is and how fast it's moving is the same thing as its ability to exhibit wave-like or particle-like behavior. They're not two mysteries, they're one. Then, in 2024, researchers at Linköping University added even more weight. They used orbital angular momentum states of photons, twisted light, to confirm that uncertainty and duality are inseparable. By entangling pairs of photons and manipulating how information was shared between them, they could directly control how wave-like or particle-like the behavior became. And if that wasn't strange enough, consider the quantum Cheshire cat experiment from 2023. Named after the grinning feline in Alice in Wonderland, this setup managed to separate a photon's properties from the photon itself. In weak measurements, the photon's polarization, the way it oscillates, traveled a different path than the photon's position. It was as if the grin existed without the cat, as if a particle's traits could be decoupled from its existence. Let that sink in. A particle's properties aren't fixed. They're contextual. They arise depending on what questions you ask and how you ask them. So what does this mean for our idea of a particle? It means the term itself might be obsolete. These aren't particles the way we imagined them in classical physics. They're not little balls moving through space. They are excitations, probabilities, mathematical constructs that act like particles when forced to and like waves when left alone. They are entities that do not exist in isolation from the observer. At its core, the double-slit experiment isn't just about slits and electrons. It's about what it means to know something. It's about the boundary between reality and measurement, between potential and fact. When you don't observe the path, the universe stays undecided. When you look, it chooses. This is not a world of deterministic certainty. It's a world of shadows, collapses, and flickers of possibility. And yet, this is the world that builds our atoms, our molecules, our very bodies. If particles don't behave like particles, are they even real? In the next chapter, we'll explore just how deep this rabbit hole goes, into phenomena so strange they defy classical cause and effect altogether. Because if a particle can pass through a wall, it has no energy to overcome. What does that say about the laws we thought governed the universe? Welcome to quantum tunneling. Imagine a ball rolling toward a hill. If it doesn't have enough energy, it rolls back. Simple, predictable. That's how the world works, or at least how it seems to. In classical physics, a particle trapped in a potential well, a valley between two hills, can't escape unless it has enough energy to climb over. That's the rule. No exceptions. But in the quantum world, the rules are different. Particles don't just sit at the bottom of the well. They blur, they smear. Their wave function leaks into places they shouldn't be. And sometimes, improbably, they appear on the other side of a barrier they had no right to cross. No energy boost, no cheat code, just there. This is quantum tunneling, and it's not just a quirky anomaly, it's one of the most essential, mind-bending and widely applied phenomena in all of modern physics. Here's how it works. Quantum mechanics tells us that particles aren't little dots. They're described by wave functions, which encode the probability of finding them at a given place and time. When a quantum object encounters a potential barrier, say a thin wall with more energy than the particle has, it doesn't just bounce back. Its wave function penetrates into the forbidden region, decaying exponentially. There's still a small, non-zero chance of finding the particle inside the barrier. And if the barrier is thin enough, or the particle light enough, that probability extends all the way through. The particle can tunnel out on the other side. No classical physics, no energy deficit overcome. Just probability, just presence. The mathematics behind this, found in the Schrödinger equation, has been tested and confirmed repeatedly since the 1920s. In fact, quantum tunneling was first proposed to explain a mystery in nuclear physics, alpha decay. How could a heavy nucleus eject a chunk of matter, a helium nucleus, without any apparent energy to do so? In 1928, George Gamow applied tunneling theory and found the results matched experimental observations beautifully. The particle wasn't climbing over the barrier, it was passing through it. Tunneling soon went from theoretical oddity to indispensable tool. In 1957, Leo Esaki built the first tunnel diode, a semiconductor device that exploits electron tunneling to switch at extremely high speeds. It earned him a Nobel Prize. Then in 1981, physicists Gerd Binnig and Heinrich Rohrer developed the scanning tunneling microscope, which uses quantum tunneling currents to image individual atoms on surfaces. This wasn't metaphorical anymore. We were using tunneling to see and manipulate the quantum world directly. Today, quantum tunneling is everywhere. It drives the nuclear fusion that powers our sun. Without tunneling, protons would never get close enough to overcome their mutual repulsion and fuse. You wouldn't be here. Neither would the light from any star. It also underpins technologies like flash memory, quantum computing, and superconducting qubits. It shows up in chemical reactions, in enzymes, in DNA proton transfers. Some theories even suggest tunneling played a role in life's origin on Earth, helping delicate molecular reactions occur in environments where they otherwise wouldn't. But for all its utility, tunneling still feels like a violation of logic. After all, how does something go somewhere it has no energy to reach? To answer that, we have to abandon the idea of a particle as a thing with a clear boundary and a well-defined path. In the quantum world, the particle is a set of probabilities. It is already slightly present in places it hasn't reached yet. The barrier doesn't block a solid object, it attenuates a wave. And the thinner the barrier, or the lighter the particle, the more of that wave sneaks through. In 2020, researchers at the University of Toronto measured how long it takes a particle to tunnel through a barrier. They used rubidium atoms and a technique known as a Larmor clock, tracking the particle's spin orientation as it passed through a laser-generated wall. The result? About 0.61 milliseconds. But here's the strange part. Lower energy particles appeared to spend less time in the barrier. That's the opposite of what you'd expect. It suggests that the tunneling process is not just probabilistic, it's temporally warped. The question of how long a particle tunnels may not have a simple answer at all. Even more controversial are claims of superluminal tunneling, suggesting that the peak of a particle's wave function may travel faster than light while tunneling. Though most physicists agree this doesn't violate causality, since no information is transmitted faster than light, the idea still unsettles the comfortable boundaries of relativity. And in 2025, a groundbreaking experiment in communications physics added a new twist. Researchers showed that ultra-cold atoms could tunnel across long distances, far beyond their de Broglie wavelength, using matter waves propagating through separated optical lattices. It shattered the conventional wisdom that tunneling only happens across short gaps. Now, suddenly, particles were leaping across space in a way that defied prior models. The quantum world had once again outgrown our assumptions. So what does all this mean for the idea of a particle? It means that the particle isn't something locked in place, waiting to collide with things. It's not a billiard ball trapped behind a wall. It's a fluid, probabilistic ripple in a wave function, something that can spread, shift, and leak through boundaries without ever fully being in the classical sense. It means particles do not follow the rules of objects. They are governed by the mathematics of uncertainty, not the mechanics of Newton, and yet we use them. We build technologies from them. We create our lives from them. All based on the idea that a thing, this thing, exists here now. But that's the illusion. Tunneling shows us that particles are not confined, that they defy location, that they can be both here and there or neither until you check. And when they do move, they don't always follow paths. Sometimes they skip space altogether. It's not just mysterious, it's deeply humbling. Because if the most basic constituents of the universe can pass through solid barriers, break cause and effect, and vanish in one place only to appear in another, then what exactly is a particle? And if we can't define that, then what are we made of? In the next chapter, we'll explore a kind of particle that takes this ambiguity even further. Particles that aren't real at all, never observed, never touched, never detected, yet somehow responsible for nearly every force in the universe, virtual particles. Particles that don't exist, but leave fingerprints everywhere. By now we've learned that particles can act like waves, pass through walls, and appear only when measured. But what if there are particles that don't even appear, not ever, yet still shape the fabric of reality? Welcome to the world of virtual particles. In quantum field theory, particles are not seen as isolated little nuggets of matter. Instead, every type of particle corresponds to a quantum field, an invisible medium stretching across all of space. What we perceive as a particle is simply a localized excitation in that field, like a ripple in a pond. But the pond is everywhere, and the ripple is the only thing we can detect. But even when nothing is visibly rippling, the fields are never still. At every point in space, even in total vacuum, these fields are fluctuating, restless, unstable, and full of brief, unobservable flickers of energy. These fluctuations manifest as virtual particles, temporary, mathematical blips that flash in and out of existence too quickly to be measured, yet leave behind very real consequences. They are called virtual because they do not satisfy the usual requirements for real particles. They cannot be detected in an experiment. They don't obey the standard energy-momentum relationship. They exist only within the scaffolding of calculations, appearing in Feynman diagrams as internal lines, mediating forces, making things happen from behind the scenes. And yet, despite never being seen, these ghostly entities are responsible for nearly everything. Every time two electrons repel one another, they are exchanging a virtual photon. That photon doesn't exist in the way a real photon does. It can't be captured, counted, or studied. But its effects are real. It carries force, information, interaction. The strong nuclear force, which binds quarks together inside protons and neutrons, is mediated by virtual gluons. The weak nuclear force that governs radioactive decay is carried by virtual W and Z bosons. Even gravity in some theories would be mediated by a virtual graviton, a particle so elusive we may never detect it, but without which our equations don't make sense. The Casimir effect is a perfect example. Place two uncharged parallel metal plates in a vacuum, very close together, and they will begin to move toward one another. seemingly pulled by an invisible force. There's no electric charge, no gravity acting on this scale, nothing we can see, but quantum field theory predicts that virtual photons, fluctuations in the electromagnetic field, exist even in empty space. Between the plates, certain wavelengths are suppressed, while outside the plates, all wavelengths are allowed. The imbalance creates pressure, pushing the plates together. It's been measured, it's real, and it's caused by particles that never existed. Then there's Hawking radiation, one of the most elegant thought experiments in physics. Near the event horizon of a black hole, quantum fluctuations produce a virtual particle-antiparticle pair. Normally, such pairs annihilate immediately, returning their borrowed energy to the vacuum. But if one particle falls into the black hole while the other escapes, the escaping particle becomes real. It radiates away. And because the black hole has lost a bit of energy, it shrinks. Over immense time, black holes evaporate because of particles that began as virtual ghosts. Some physicists have taken this even further. Schwinger pair production, for example, proposes that strong electric fields can rip apart the vacuum itself, converting virtual particles into real ones. It's been theorized and modeled, though not yet observed directly. Still, it suggests that under the right conditions, the vacuum is not empty. It's a seething sea of potential, of particles waiting to be born. But this raises a deeper question. If virtual particles are just mathematical artifacts, tools for calculating probabilities, then do they exist? Or are we just fooling ourselves with clever symbols and convenient language? There's a fierce debate about this. Some physicists argue that virtual particles are nothing more than bookkeeping tricks, side effects of perturbative expansions in our equations. They're not particles at all, just blips in the math. Others argue that if something produces real, measurable effects, then it's fair to say it has some kind of reality, even if it can't be isolated or observed. It's not a settled issue, and that's what makes it so fascinating, because if virtual particles are not real in the traditional sense, but are responsible for every force we feel, then what does that say about the idea of real to begin with? How do you define existence in a universe where the most fundamental ingredients may never be seen, only inferred? In the 2024 paper on Schwinger pair production, researchers examined the quantum phase structures that govern virtual particles in vacuum tunneling events. They found that the behavior of these ghostly pairs depends not just on local energy conditions, but on the entire phase landscape of the field, akin to the Aharonov-Bohm effect, where particles are affected by potentials in regions they never physically enter. The message is clear. In quantum mechanics, influence doesn't require presence. Causality doesn't require contact. Interaction doesn't require existence, at least not in the way we understand it. This begins to paint a picture of a universe where the building blocks of reality are less like Lego bricks and more like ripples in a storm. Ephemeral, emergent, dependent on context. Virtual particles are part of that storm. They are the fingerprints of the quantum vacuum, an ocean beneath what we used to think was empty space. And perhaps most astonishing of all, the standard model of particle physics, the most successful theory we've ever created, works only because of virtual particles. Without them, the equations don't balance. The predictions fail, the model collapses. They are not optional, they are the glue. But they are also invisible, untouchable, flickering in and out of the calculation like shadows that leave dents in reality. So once again, we're left with the question, what is a particle? Is it something we can see, something we can hold, something that must appear on a screen to be considered real? Or can something that's never been detected, never truly observed, still be said to exist if its effects are everywhere? In the next chapter, we'll explore the idea that perhaps particles are not objects at all, but events, temporary spikes in something deeper, vibrations in the invisible fields that make up the entire universe. Because if a particle is nothing more than a ripple, then what's doing the rippling? And is that what's real? By now, the cracks in the classical idea of a particle are gaping. They behave like waves. They tunnel through barriers. Some are virtual, never directly observed but mathematically necessary. So we arrive at a natural question. If particles aren't the foundation of reality, then what is? Enter quantum field theory. It's not a household term, but it's the most successful framework in all of physics. It explains electromagnetism, the strong and weak nuclear forces, and nearly every interaction we've ever measured. It's the backbone of the Standard Model. And at its heart is a radical idea. Particles don't exist, not as fundamental things. Instead, the universe is made of fields, continuous, invisible, stretching across all of space and time. For every kind of particle, there is a corresponding field. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. A quark, a ripple in the quark field. These fields are always there, even in empty space. What we call a particle is just a localized excitation, like a tiny temporary bump on a vast unseen ocean. And these ripples don't move through space on top of the field. They are the field, disturbed at a point. There is no object traveling from place to place. Instead, the field rearranges itself momentarily, and we experience that as a particle being born, moving, interacting, and disappearing. It's a hard shift to make. Our minds are wired for objects. We think in terms of things. But quantum field theory doesn't care about our intuitions. It tells us that everything we see, every atom, every flash of light, every breath, is a set of interacting field vibrations, nothing more. And yet, this picture is astonishingly precise. The electron's magnetic moment, predicted by quantum electrodynamics, agrees with experiment to better than 1 part in a trillion. No other theory in history has achieved this level of accuracy. And it only works when we treat the electron not as a particle, but as a ripple in a quantum field. These ripples can be created or destroyed. They can combine, annihilate, or transform. They obey conservation laws, but they are not persistent objects. They are events, appearances. The particle doesn't fly through space. It appears, interacts, then dissolves back into the field that spawned it. This is why, in collider experiments like those at CERN, we don't see particles. We see traces, blips, spirals, scattering patterns. What we're really seeing is the aftermath of energy rippling through overlapping fields, collapsing briefly into interactions, then vanishing again. In this view, empty space isn't empty at all. It's alive with potential. Even in a perfect vacuum, the fields remain, vibrating with zero-point energy, birthing virtual particles, influencing forces. This is why even nothingness has structure, why the Casimir effect works, why Hawking radiation makes sense. The vacuum isn't void, it's pregnant with possibility. The fields themselves are fundamental. The particle is just what happens when you poke the field in a particular way. But how do we poke a field? With energy. Imagine the field as a calm sheet of water. Toss in a stone and ripples spread. The stone is energy, the ripple is a particle. The shape, duration, and frequency of the ripple determines what kind of particle it is, its mass, charge, spin. But the water is still the underlying reality. And this explains another strange quantum truth. Particles of the same type are completely identical. Every electron in the universe has the exact same mass, charge, and spin. Why? Because they're not made of components. They're not machines. They're not individual things. They're all the same ripple in the same universal field. They are indistinguishable because they are not separate entities. They're expressions of a single structure. This idea reshapes how we think about matter. Matter is not made of little building blocks. It's made of field excitations, temporary conditions in something deeper. When we say we're made of particles, what we really mean is that our bodies are patterns of energy riding on a sea of quantum fields, stabilized by forces we barely understand. And that leads us to an even deeper truth. Particles don't have identity. They don't have a continuous existence. An electron doesn't move from point A to point B. Instead, the electron field becomes excited in one place, then excited again somewhere else, with the intermediate state defined by probabilities. There's no little marble traveling in between. There's only the field and the mathematics that governs how its excitations evolve. This is why experiments like quantum teleportation work. It's why particles can become entangled and act as if they're linked across vast distances. The field is not local, it's global. It stretches across space. And when you disturb it in one place, the effects can ripple instantly elsewhere, not by transmitting information faster than light, but by reshaping the shared underlying structure. In 2012, the discovery of the Higgs boson confirmed this picture. The Higgs field pervades all space. Particles gain mass by interacting with it. They are not given mass like a gift. They acquire it by dragging through a field that resists their motion. The more they interact with the Higgs field, the more massive they become. Even mass, then, is not an intrinsic property. It's an emergent behavior, a measure of how stubbornly a particle's ripple disturbs the field. So what does this mean for us? It means that what we think of as matter is, at its core, a pattern in a field, a temporary glitch, a brief, local shimmer in a vast ocean. There are no beads of matter strung together like pearls, no indivisible points that form a foundation. There are only fields. And we are their music. Quantum field theory doesn't give us particles, it gives us relationships, structures, symmetries. It gives us the rules for how energy moves through space and time, and how those movements produce what we perceive as things. But those things, those particles, are illusions. Useful, measurable, meaningful illusions. In the next chapter, we'll zoom in on the ones we know best, the particles that make up everything around us, quarks, leptons, neutrinos, electrons, the particle zoo of the Standard Model. We'll see how these so-called building blocks behave and why, even among the smallest known entities, solidity is nowhere to be found. For generations, science has searched for the indivisible. From the Greek atomos, meaning uncuttable, to today's particle accelerators hurling matter into itself at near light speed, the goal has been the same: to find the ultimate foundation, the bricks that build everything, the end of the line. And for a time, we thought we'd found it. Protons and neutrons in the atomic nucleus, electrons orbiting outside, three simple pieces. The structure of the atom was elegant, digestible, a miniature solar system hiding inside every object. But just like the Bohr model of the atom, that was only the beginning of the story. Because protons and neutrons aren't fundamental at all. They're made of quarks, tiny hyperenergetic packets of charge, spin, and color. Yes, color. Not in the visual sense, but a quantum property related to the strong nuclear force. There are 6 known quarks: up, down, charm, strange, top, and bottom. Each comes in 3 colors and they never appear alone. Ever. Quarks are permanently confined within larger particles like protons and neutrons. Try to pull one out, and the energy required to do so simply creates more quarks. It's like trying to separate 2 ends of a rubber band. The further you stretch, the more resistance you get, until the band snaps and new bands are formed in its place. This confinement is due to the strong nuclear force, the most powerful force in the known universe. And it's mediated by gluons, massless, chargeless particles that constantly shuttle between quarks, gluing them together with such tenacity that quarks are never observed alone. In fact, no one has ever seen a free quark. We know they're there because their effects, like the scattering patterns in deep inelastic collisions, match the predictions of quantum chromodynamics, the field theory that governs quark behavior. But in a very real sense, quarks are more inferred than observed. They are theoretical necessities, not isolated things. And that already puts their reality on shaky ground. Then there's the electron, arguably the most famous particle of all. Unlike quarks, electrons are considered fundamental. They don't seem to be made of smaller parts. They carry charge, They have spin, and they orbit atoms, or rather, they form probability clouds around nuclei, shaping chemistry, electricity, and life. And yet they too defy the idea of a solid object. Electrons have no internal structure. They are point-like, infinitely small in current models, and yet they exhibit wave-like properties. They interfere, diffract, superpose. They pop in and out of existence in quantum fluctuations. The cloud of virtual particles surrounding an electron affects its behavior so much that it must be dressed in self-energy corrections just to match what we observe. Neutrinos go even further. These ghostly particles pass through trillions of atoms every second, barely interacting. They have mass, but so little that we didn't even know they had mass until the late 1990s. They come in three types: electron, muon, and tau, and they can morph between them as they travel, a phenomenon known as neutrino oscillation. No one knows exactly why they're so light or why they exist at all, but without them the universe would be unrecognizable. And then there's the Higgs boson, the newest member of the family, discovered in 2012 after decades of searching. It's not just a particle, it's the signature of a field, the Higgs field, that fills all of space. Other particles acquire mass by interacting with it. The stronger the interaction, the more massive the particle. If the Higgs field didn't exist, nothing would have mass. Quarks wouldn't form protons. Electrons wouldn't orbit nuclei. Atoms wouldn't exist. Neither would you.
And what do all of these particles, quarks, leptons, bosons, actually look like?
Nothing. They don't have surfaces. They don't bounce off each other like billiard balls. They're not in a place until measured. They don't even exist between measurements in the way we typically understand the word. They are excitations, patterns, temporary arrangements in the fields that underlie all things. Even their identities are mutable. In high-energy environments, particles can transform into other particles. Quarks become leptons. Photons become electron-positron pairs. These aren't shapeshifters. They're field configurations rearranging themselves under the rules of conservation. Mass, energy, spin, charge, all conserved. But the players themselves, swapped, changed, evolved. In recent years, the boundaries of what we think we know have continued to blur. In 2024, experiments at the Large Hadron Collider detected quantum entanglement between top quarks, particles that decay so quickly they barely exist. And yet, in the split second they flicker into being, their quantum states remain linked. This means that even the most short-lived, energetic particles in the Standard Model obey the same weird rules as their lighter cousins. They're part of the same field-based, non-local reality. What emerges from this particle zoo is not a sense of solidity, but a profound sense of impermanence. The more we look, the less we find. The deeper we dig, the more reality begins to look like a shifting mathematical tapestry, waves and probabilities and fields in constant motion. What we call particles are not little bits of stuff. They're events, interactions, moments when the underlying fields momentarily coalesce into something we can detect. This changes everything. Because if protons and neutrons are made of quarks, and quarks are inseparable from their field, and electrons are excitations with no size, and neutrinos are barely there at all, what is matter? What is this world made of? The answer is both liberating and unsettling. Nothing solid, nothing fixed, nothing that exists independently of everything else. Only patterns, only energy, only the tremble of a deeper fabric. In the next section, we'll explore just how that fabric behaves, how the very act of not observing a particle allows it to be in multiple states at once, to spread out, to interfere with itself, to exist as a wave of possibilities until the universe forces it to choose. We're entering the strange and shadowy realm of quantum superposition, where reality is not what it is, but what it might be. Picture this. You flip a coin, cover it with your hand and ask, is it heads or tails? Intuition says it must be one or the other, even if you don't know which. That's the classical view. Uncertainty is just a matter of ignorance. But in the quantum world, until you look, the coin isn't either. It's both and neither. It's heads and tails. It exists in a ghostly blend of all possible outcomes. This is superposition. In classical terms, it's madness. In quantum mechanics, it's a fundamental truth. At the quantum level, particles don't choose a state until they're forced to. Until you measure them, they exist in a superposition, a simultaneous existence of all possible configurations. Position, momentum, spin, even identity. They are described not by concrete attributes, but by a wave function, a mathematical map of probabilities, not certainties. And as long as no one's looking, that wave function spreads, it evolves, it explores every possible path. But the moment you observe it, when you interact with it in a way that causes measurement, it collapses. One outcome snaps into reality, the others vanish like mist in morning sun. This isn't just theoretical, it's been shown in experiment after experiment. The double-slit experiment we covered earlier is a textbook example. When not observed, each particle travels through both slits, creating an interference pattern. When you place a detector at the slits, the pattern disappears. The particle chooses a path. Superposition ends. Measurement kills the wave. But superposition goes far deeper than just which slit a particle uses. In 2012, researchers performed a quantum eraser experiment, a version of the double-slit setup where which path information could be erased after the particle had passed through the slits. Strangely, if the path information was erased, the interference pattern returned, even though the particle had already hit the screen. It was as if the act of erasing the measurement retroactively changed the past. Reality, it seemed, didn't commit to a history until the observer forced its hand. This isn't science fiction. This is laboratory reality, and it upends everything. Because superposition doesn't just mean a particle is in multiple places, it means it has multiple states of being, multiple potential identities, a spin-up electron and a spin-down one, a particle in two locations, a photon taking two paths, a qubit in a quantum computer being both 0 and 1 at once. This is what powers the strange potential of quantum computing. Unlike classical bits, which are binary, qubits leverage superposition to hold multiple states simultaneously. With just a handful of qubits, a quantum computer can explore vast combinations of solutions in parallel, not because it's faster, but because it's stranger. It doesn't solve problems by working through them. It samples every path at once and collapses on the best outcome. But with this power comes fragility. Superposition is a delicate thing. Interact with it too soon, introduce even the tiniest disturbance, and it collapses. That's why quantum systems must be shielded from heat, light, vibration. The universe is a noisy place, and decoherence, the decay of superposition into a single state, happens at the slightest nudge. So what does this mean for particles? It means they are not things with permanent properties. An electron does not have a position until you ask. A neutron does not have a decay time until it's measured. Even identity can be in flux. A neutrino oscillates between flavors as it travels, existing in a superposition of states that don't resolve until interaction. It also means that reality, at its core, is probabilistic, not deterministic. It's not just that we don't know what's happening, it's that nothing definite is happening until the wave function collapses. The universe doesn't roll dice in secret. It is the dice, and the outcome isn't written until someone opens the box. Schrödinger's cat is the infamous metaphor, a cat placed in a sealed box with a quantum trigger that may or may not kill it, depending on the decay of a radioactive atom. Until the box is opened, the cat is both alive and dead. Not as a joke, but as a literal expression of superposition applied to the macroscopic world. Of course, cats aren't particles, but the principle holds. And experiments in quantum biology suggest that even large, complex systems, like enzymes or even bird navigation, may leverage superposition before collapsing into classical outcomes. Life, it turns out, may have learned to dance on the razor's edge between probability and reality. In 2021, scientists at Korea's Institute for Basic Science conducted controlled experiments to quantify a photon's wave and particle character. By carefully adjusting the probability distributions of photon emission and entanglement, they showed that the photon could exist in a tunable mix of both behaviors, a kind of dial between wave and particle. This reinforced what many suspected. That superposition isn't a byproduct of our ignorance. It's a fundamental, measurable property of nature. But what is it we're actually observing when we measure? Is the wave function real or just a useful fiction? This question has haunted physicists for decades. Some believe the wave function is simply a tool, a way to calculate probabilities. Others argue that it is reality itself, that what we perceive as definite outcomes are just one collapsed branch of a much wider multiverse. The many worlds interpretation proposes that all outcomes happen, but in different branches of reality. When you observe the cat, it doesn't choose to live or die. You just become entangled with the version of the cat that lived or died. Every measurement, every interaction creates a split in the fabric of existence. Reality doesn't choose. It multiplies. It sounds wild, but then again, so does everything else we've covered. So where does this leave our idea of a particle? It leaves it hollow. A particle is not a thing that is. It is a probability cloud, a maybe, a could be. It exists in every form it might take until you observe it. And even then, what you see is only one shadow from 1,000 possible outcomes. It is the ghost of a question frozen into a single answer. That's not how we learned about the world as children, but it's how the universe actually works. In the next section, we'll explore the flip side of superposition, entanglement. If a particle can be in many states, then what happens when two particles share a state? When their properties become inseparably linked across space and time? What happens when changing one affects the other instantly? Welcome to Spooky Action at a Distance. Welcome to quantum entanglement. If superposition tells us a particle can be in many states at once, entanglement takes that logic and stretches it across the universe. It says, not only can particles exist in multiple potential realities, but two particles can become so deeply connected that measuring one instantly determines the state of the other, no matter how far apart they are. They can be on opposite ends of a galaxy and yet behave as if joined by an invisible thread. This isn't science fiction. It's the most tested, most bizarre, and most undeniably real aspect of quantum physics. Einstein famously hated it. He called it spooky action at a distance, a phrase now etched into the history of physics. To him, the idea that one particle could affect another instantly, faster than light, outside the bounds of space-time, was absurd. It had to be a mistake, a symptom of an incomplete theory, hidden variables perhaps, some secret mechanism we didn't yet understand. But the experiments kept coming, and the results kept saying the same thing. Entanglement is real. Here's how it works. Take two particles, say electrons, and bring them together in just the right way so their quantum properties become linked. Their spins, for example, might be set up so that if one is measured as up, the other must be down. This doesn't mean they were up and down before measurement. It means they were both in a state of superposition, undefined, until you observed one. The moment you measure it, its partner is forced to snap into the corresponding opposite state. Instantly, no signal passed between them, no light beam, no vibration, just knowledge. One particle knows what happened to the other, and this holds no matter the distance between them. Entangled photons have been separated by hundreds of kilometers, even bounced off satellites in orbit, and still behave as one system. In 2017, a Chinese satellite named Mikius beamed entangled photons between ground stations over 1,200 kilometers apart, and they passed the test. Quantum mechanics held. Einstein's objections did not. So what's really going on? One interpretation is that entanglement doesn't involve a signal at all. It's not one particle sending information to the other. It's that they were never two particles to begin with. They were a single quantum system, described by a single inseparable wave function, even across space. In this view, space is not what it seems. The particles aren't communicating faster than light. They're not separated in the way we imagine. Entangled particles are like opposite ends of the same object. Measure one, and you're simply revealing something about the whole. This erases the boundary between them. It turns particle into a misnomer. Entanglement shows us that identity itself can be shared, that parts of reality can be fundamentally indivisible, not just in structure, but in information. And information, it turns out, may be the real currency of the quantum world. This is the foundation of quantum teleportation, not teleporting mass like in science fiction, but transferring quantum states. In 1997, physicists achieved the first successful teleportation of a quantum state across a short distance. Today, it's routine in labs. By entangling two particles and using classical communication, you can destroy the state of one particle and recreate it exactly in another. The information doesn't travel, it simply appears where it needs to be, as if it had always belonged there. But entanglement isn't just a scientific curiosity. It's the engine behind quantum encryption, quantum computing, and possibly the very structure of space-time itself. In recent theoretical work, some physicists have proposed that the geometry of space, the fabric of reality, is woven together by entanglement. That the strength of entanglement between quantum fields determines how close or far things feel. That distance is not a fundamental property, but a byproduct of how entangled regions of space are. This is the ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind. It suggests that entangled particles may be connected by tiny wormholes, Einstein-Rosen bridges, that stitch the universe together at the quantum level. Two particles, entangled and separated, might literally be linked through a fold in space we can't see. If true, this would collapse the division between quantum mechanics and general relativity. It would mean that gravity and geometry emerge not from matter, but from information. And the implications are staggering. Because if entanglement creates space, then perhaps nothing is truly separate. Perhaps everything that exists is, at some level, entangled with everything else. Perhaps there are no islands, only waves in the same ocean. In 2024, the Large Hadron Collider took another step toward this strange future. For the first time, entanglement was observed between top quarks, massive particles that decay in less than a trillionth of a second. That even these particles, born in the chaos of high-energy collisions, could become entangled before disintegrating, suggests that quantum connectivity is not a rare exception. It is everywhere. It is instant. It is unavoidable. So what does this do to our idea of a particle? It vaporizes it, because once you accept that a particle's state can depend on a distant partner, it's no longer meaningful to think of it as an isolated entity. It's not a self-contained thing, it's part of a web, a node in a pattern, a single pulse in a song being played across the universe. Entanglement shows us that reality is not made of parts, it's made of relationships. What something is depends on what it's connected to. There is no absolute, only context. You can no longer ask, what is this particle doing, without also asking, what is its entangled partner doing? The answer doesn't live in one place, it lives between them. And once again, we're forced to admit, the term particle is woefully inadequate. It evokes something localized, separate, countable. But in quantum physics, nothing is ever just itself. Everything is suspended in a web of potential, co-authored by distant, unseen influences. Even the act of measurement, of knowing, ripples outward, collapsing possibilities, entangling you with the thing you observe. So perhaps in some ineffable way we are entangled too, with the matter we study, with the cosmos we question, with each other. In the next section, we'll peer into perhaps the strangest result of all, particles that arise not from anything material, but from the void itself, from empty space, from nothing. Virtual particles hawking radiation, Zero-point energy, the physics of the vacuum. Because if particles can be born from nothing, then perhaps nothingness is the most real thing of all. We tend to think of empty space as just that, empty. A cold, black void between the stars, a backdrop, a vacuum. But quantum physics tells a different story. In this world, the vacuum is not silent. It's a seething, restless ocean of potential. Even when you strip the universe of matter, light, heat, and motion, when you reach the absolute zero of nothingness, you haven't reached true emptiness. Instead, you've opened the door to one of the most active, unpredictable, and bizarre layers of reality. This is the quantum vacuum. At the heart of quantum field theory lies a surprising truth. The ground state of any field, the lowest energy state, is not zero. Even in nothing, the field fluctuates. These fluctuations are unavoidable, irreducible, and real. They're known as zero-point energy. Picture a completely still pond, no wind, no ripples. But in the quantum version, the surface is never flat. It jitters, it twitches. At every point, there's an incessant hum. These aren't waves moving across the pond. They're microbursts, foam bubbling up from beneath, never fully seen but always present. These fluctuations give rise to virtual particles, short-lived pairs of particle and antiparticle that pop into existence, exist for a blink of time, and then annihilate back into the void. They can't be measured directly. They break the usual rules of energy conservation, but only for brief intervals, allowed by the Heisenberg Uncertainty Principle, which says the shorter the time a fluctuation exists, the less it has to obey energy strictness. dE.dt greater than or equal to h/2. That's the loophole. That's what makes the impossible possible. But make no mistake, these virtual particles, though never directly observed, have real effects. In 1948, Dutch physicist Hendrik Casimir predicted that if you placed two uncharged metal plates extremely close together in a vacuum, they would attract each other. Why? Because virtual photons, fluctuations of the electromagnetic field, exist everywhere, but between the plates, only certain wavelengths can fit. The imbalance in energy pushes the plates together. This is the Casimir effect. It's been measured. It's real. Empty space has pressure. Then there's Hawking radiation, the strange process by which black holes, those ravenous monsters of gravity, slowly evaporate. Stephen Hawking proposed that near the event horizon, virtual particles are constantly forming. Normally they annihilate, but if one falls into the black hole while the other escapes, the escaping particle becomes real. To conserve energy, the black hole must lose mass. Over eons, it shrinks and fades. A black hole, an object from which not even light can escape, can leak particles. And it's all because the vacuum refuses to be empty. In more recent experiments, scientists have simulated Hawking radiation in laboratory settings using analog systems like Bose-Einstein condensates and optical waveguides. While not direct black holes, these systems confirm the mechanism. When spacetime is curved or energy fields are extreme, vacuum fluctuations become visible. The void reveals itself. In 2025, a study in communications physics shook up long-held beliefs. Researchers demonstrated that ultra-cold atoms could tunnel across vast distances in optical lattices, not by moving through the intervening space, but by leveraging the structure of the quantum vacuum. It was as if atoms could exploit the foam of nothingness to disappear in one place and reappear elsewhere. No path, just presence. And then there's Schwinger pair production, a predicted but not yet directly observed process in which a strong electric field can rip apart the vacuum, birthing real particle-antiparticle pairs. In other words, energy alone, applied correctly, can summon matter from the void. This isn't mythology, it's quantum electrodynamics, and it leads to a staggering conclusion. Particles are not permanent residents of the universe. They are temporary configurations of energy. They can be created and destroyed. They can emerge from silence and dissolve into it. They are not the foundation of everything. They are the surface foam of something deeper. It also means that nothing is not the absence of something. It is the presence of potential. The vacuum is not dead space. It is the primordial engine, the stage not on which the play unfolds, but from which the actors arise spontaneously. And if this vacuum has energy, and it does, it also has consequences. Zero-point energy is thought to contribute to the cosmological constant, the mysterious factor that drives the accelerated expansion of the universe. Dark energy, as we call it, may be nothing more than the accumulated push of quantum fluctuations writ large, not a force, not a substance, just the vacuum, exhaling. So when we ask, are particles even real? The vacuum stares back with a smile. Because in a very real sense, the particles we see, measure and touch are simply brief disturbances in an ocean that never rests. They are the exception. The vacuum is the rule. In quantum field theory, this vacuum structure is deeply woven into the identity of particles. The fields themselves define how particles behave, not by what they are, but by how they interact with this ever-shifting background. Even mass, once thought to be an intrinsic property, is determined by how a particle moves through the Higgs field, another ever-present layer of the vacuum. So the identity of a particle is not written into the universe, it's negotiated moment by moment with the vacuum itself. And what does that make us? We are temporary structures of energy, coherent patterns in the foam. Organized fluctuations stabilized long enough to ask the question, what are we made of? And if particles come and go, if reality is stitched from emptiness, if the vacuum itself has memory, structure and pressure, then the idea of a particle as a thing becomes laughable. It's not a thing, it's an event, a ripple, a moment. In the next section, we'll explore what this means for our understanding of time, causality, and the very meaning of existence. Because once you realize particles aren't solid, aren't permanent, and aren't even necessary, you start to question everything, including whether now is even real. If you could pause the universe right now, freeze every atom, every photon, every fluctuation, what would you have? The illusion of now. Because at the quantum level, the present moment isn't a defined state. It's not a snapshot of particles in fixed positions, frozen in space like marbles on a table. It's a blur, a set of probabilities, a fuzz of superpositions, entanglements and fluctuations that don't fully resolve until interactions force them to. In other words, even now is uncertain until it's observed. Time in classical physics is a flowing river, a steady march from past to future, with each moment giving birth to the next. But quantum mechanics doesn't support this picture. In its equations, time is treated differently than space, but not more real. The wave function evolves deterministically, but measurement introduces abrupt changes, jumps, collapses, moments that break the flow. And this presents a paradox. In everyday life, we assume that the future doesn't exist yet and the past is gone. The present is all that's real. But in quantum mechanics, the wave function stretches across time. It doesn't just describe where a particle might be. It includes when, before, during, after. It's all baked into the math. Time isn't something that flows. It's a landscape we traverse by interaction. The idea becomes even more jarring in delayed choice experiments, where the outcome of a measurement made now seems to change the behavior of a particle that occurred in the past. The photon passes through the slits, but whether it behaved like a wave or a particle seems to depend on a decision made after it already hit the screen. This isn't an illusion. It's been replicated, confirmed, debated, and still stands. The past isn't fixed. It's conditional. It depends on how we choose to interact with the present. Causality, the chain of this causes that, fractures. It doesn't break exactly, it frays. It becomes context-sensitive, observer-dependent. Events no longer have a clean ordering. Instead, they live inside probability clouds, codependent on measurement. In 2020, a team at the University of Toronto used rubidium atoms and a Larmor clock to measure how long particles spend inside a tunneling barrier. They found that lower energy particles tunneled faster, spending less time inside the barrier than their high-energy counterparts. It was as if, the less likely the event, the quicker it happened. The relationship between energy, time, and outcome twisted into something non-linear. Time didn't behave the way clocks suggest. It bent toward probability. At the quantum level, the arrow of time blurs. Entropy still increases. Systems evolve from order to disorder, but quantum systems, left unmeasured, can evolve forward or backward in time according to the same rules. The fundamental equations of quantum mechanics don't favor a direction. They are time-symmetric, reversible. So why do we remember the past, not the future? Why does the tea only spill out of the cup and never back in? Because of measurement, because of entanglement, because every interaction decoheres possibilities into history. Observation acts like a ratchet, locking the universe into one timeline. The others fade, not because they were never real, but because they were never reinforced. In quantum terms, the present is a crossroads where all possible pasts and all possible futures converge. What becomes real is not what was, but what coheres, what fits, what interacts in a way that leaves a record. And yet, even those records are fragile. Particles decay not with a predictable clock, but according to probability curves. A muon might last for 2.2 microseconds on average, but any individual muon might last longer or vanish sooner. There's no ticking inside it, no gears, just chance, just the sudden flip of the field, and it's gone. So what are we to make of all this? If a particle has no fixed position, no fixed identity, and no fixed timeline, what is it? Perhaps nothing on its own. Perhaps a particle is simply a momentary alignment of field, energy, and context, a pattern that holds long enough to make meaning, then dissolves. It is not a marble flying through space. It is not a clock ticking forward in time. It is a shimmering interference of probabilities, momentarily collapsing into something measurable. And time, what we feel as seconds passing, isn't the motion of particles, but the fading of superpositions, the narrowing of wave functions, the thinning of possibility. When enough uncertainty has resolved, we call it a second. But underneath, time may be no more fundamental than temperature or pressure, emergent, not absolute. This redefines what it means to exist. You don't exist because you occupy a point in space at a given time. You exist because your quantum state persists long enough to interact, to remember, to entangle with others. You exist as a process, not an object, not a place, not a timestamp. That's what particles are too. They don't endure like stones. They emerge like lightning, bright, brief, and contingent. And if time itself is slippery, then permanence is a myth. So when we speak of elementary particles, we are describing the most stable processes in nature. Patterns in the field that tend to recur, to resonate, to self-reinforce. They are not things, they are happenings. Reality is not a stage with actors. It is an improvisation, a jam session of probability, coherence, and collapse. And you? You are a pattern too. A grand, entangled, self-aware fluctuation in quantum fields, spanning billions of atoms, trillions of interactions, all coordinated by a thin thread of memory that calls itself a name. Particles don't live in time. Time lives in particles, and that, more than anything, may be why they aren't real in the way we once imagined, but are infinitely more wondrous than we ever believed. Suppose you want to know exactly where a particle is. You shine a light on it, detect it, trap it, pinpoint its position with greater and greater precision. But something strange happens. The more precisely you fix its location, the less you know about how fast it's moving. Its momentum becomes fuzzier. Try the reverse, measure its momentum exactly, and its position slips away. You can never know both perfectly at the same time. This is not a problem with your tools. It's not a failure of technology. It is a law of nature. The Heisenberg Uncertainty Principle isn't just a technical limit, it's a philosophical earthquake. It says that reality doesn't allow total knowledge, that even in principle, the universe won't give you everything. You can measure this or that, but never both. You must choose which question to ask, and in choosing, you erase the other answer. This principle isn't limited to position and momentum. It applies to energy and time, spin components, particle paths. It saturates all of quantum mechanics like a background hum. It governs how long a virtual particle can borrow energy from the vacuum before vanishing. It defines how sharply a particle can exist in time before its frequency blurs. And most importantly, it connects directly to wave-particle duality. In 2014, a team of physicists published a study in Nature Communications showing that wave-particle duality is not a separate mystery. It's just uncertainty in disguise. The more clearly something behaves like a particle, the less wave-like it becomes, and vice versa. The interference patterns of waves and the localized detections of particles are not dual identities. They are complementary expressions of what cannot be simultaneously known. In other words, duality and uncertainty are the same wound, viewed from different angles. But this goes beyond a clever mathematical rule. It forces us to reconsider what knowing even means. In the quantum realm, knowledge isn't passive. You don't just find out where a particle is, you create the condition in which that particle becomes local. Until then, there is no definite there. The act of measurement doesn't reveal a hidden truth. It chooses a truth. Observation isn't discovery, it's participation. And this leads to an unsettling conclusion. The observer matters, not because we are special, not because consciousness is magical, but because any interaction that extracts information, whether by a human, a camera, or a stray atom, is a measurement. And every measurement rewrites the rules of the game. It collapses superposition. It extinguishes alternatives. It gives shape to the shapeless. We are not outside the system, looking in. We are inside the wave function, shaping it. This is why physicist John Wheeler described the universe not as a static object, but as a participatory process. The cosmos is not a cathedral built from bricks. It is a conversation. A chain of yes or no questions asked by particles, fields, and observers, each answer collapsing possibility into reality. And when that possibility collapses, it leaves scars. The process of knowing something, of reducing uncertainty, extracts energy. It disrupts coherence. It causes entropy to rise. In quantum computing, the loss of superposition due to measurement is the greatest threat to calculation. To know is to destroy the alternatives. In a very real sense, knowledge costs. Even logic begins to fray under this pressure. In quantum logic, the law of the excluded middle no longer holds. A particle can be spin up and spin down, not merely either or, but both until. Statements that would be contradictions in classical logic become perfectly valid in quantum theory. The entire framework of truth shifts. It's not about what is. It's about what can be inferred given what was measured. And the deeper we probe, the more delicate this balance becomes. In cutting-edge quantum experiments, researchers now routinely probe uncertainty itself. By performing weak measurements, barely disturbing the system, they can extract information without full collapse. But the trade-off is steep. The more gentle the measurement, the less clear the answer. You can whisper to the universe, but it will only whisper back. This makes reality feel conditional. Not because it's unreal, but because it's built from constraints, from the limitations of what can be jointly known, recorded, or remembered. The world isn't made of stuff, it's made of structured ignorance, and yet there is something liberating in that. If everything we call a particle is just a collapse of probabilities, an answer to a cosmic question, then every moment of existence is a kind of revelation. Every photon absorbed, every electron detected, every atom bound in a molecule is the result of the universe choosing something out of many possibilities to become real. We are walking through a fog of uncertainty, catching glimmers of what might be and calling those glimmers facts. But those facts are shadows, brief certainties in a deeper ocean of potential. And so to ask whether particles are real is to miss the point. They are real only when they must be. They are answers to questions the universe didn't avoid. And if we accept that, if we accept that the fundamental building blocks of the world are not things, but limits on knowledge, then we begin to see the cosmos differently. Not as a machine, but as a language. Not as a puzzle, but as a negotiation. It means we don't live in a universe made of particles. We live in a universe made of questions. And we are part of the answering. In the shadowy intersection of physics and philosophy, one question refuses to stay silent. If observation collapses a quantum system, what does that say about the observer? For decades, physicists have debated whether consciousness has anything to do with quantum measurement. Does a conscious mind cause collapse? Or is observation just any interaction that transfers information from atom to atom, photon to detector? Most modern physicists lean toward the latter, and yet the deeper we go, the more slippery the boundary becomes. At its heart, quantum mechanics doesn't say that a system is in a particular state. It only tells you what you can expect when you observe it. Everything else, the superpositions, the uncertainties, the entanglements, is invisible to direct perception. It only becomes real when the system interacts with something else in a way that produces a definite outcome. A click in a detector, a mark on a screen, a record. But what makes a record a record? Is it enough for a photon to bump an atom, change its spin and vanish? Or must that change be amplified, stored, noticed? Is there a threshold, a moment when potential becomes event and event becomes experience? This is where things grow uneasy, because while we know detectors can collapse wave functions and even single molecules can decohere superpositions, there's something fundamentally different about awareness. Awareness doesn't just observe, it remembers, it models, it reflects. It brings continuity to what would otherwise be a cascade of disconnected interactions. That's why some thinkers, from Eugene Wigner to John von Neumann, speculated that consciousness might not merely observe the universe, it might participate in bringing it into being. Not in a magical sense, but in a structural one. If the universe is an information system, then consciousness is its recursive node, the place where information loops back on itself. But even without invoking consciousness as a cause, it's clear that quantum mechanics changes the role of the observer. In classical physics, observers are irrelevant. You can model a system completely without ever considering who's watching. But in quantum mechanics, the observer is baked into the theory. Observation isn't passive, it's participatory. So the real question isn't, does the observer create reality? It's this: can anything be said to exist independently of being observed, measured, or entangled with something else? Quantum mechanics suggests, not really. There is no detached reality waiting in the wings. There is only the vast probability structure of the wave function, unfolding according to deterministic laws until something, a detector, a molecule, a mind, forces it to make a choice. The realness of particles is not a static property, it is an emergent phenomenon. It emerges in the act of observation, and that realization bleeds into us. Because we are not passive observers of the world, we are systems within it. We are made of particles, of fields, of wave functions. Our thoughts are patterns in electrochemical circuits. Our perceptions arise from entangled states, collapsing billions of photons into a coherent picture of now. We are part of the quantum machinery we're trying to understand. In 2025, new research into quantum brain models revived old questions. While classical neuroscience explains much of cognition, it doesn't easily account for subjective experience, what philosophers call qualia. Some researchers propose that consciousness might arise not despite quantum uncertainty, but because of it. That coherence, entanglement, and collapse at small scales could give rise to awareness at large scales. The Orch-OR theory, championed by Roger Penrose and Stuart Hameroff, suggests that quantum events inside microtubules, tiny structures within neurons, may underlie consciousness. It's speculative, controversial, and fiercely debated. But even if wrong, it points to a tantalizing possibility, that mind and matter are not separate, but expressions of the same quantum substrate. So if particles are not things, but events, and minds are not observers, but collapses, then perhaps the universe is not a stage, but a song, a symphony of possibility with consciousness as one of its harmonics. We often think of physics as removing the magic from the world, but quantum physics, paradoxically, re-enchants it. Not by adding supernatural forces, but by reminding us that reality is not fixed. That observation matters. That possibility is baked into the bones of existence. It means that every act of seeing, thinking, measuring, or remembering is part of the grand process of the universe knowing itself. The observer and the observed are not separate, they are reflections. And so, in asking whether particles are real, we must also ask whether we are, whether there's a clear line between what's out there and what's in here, whether thingness is a useful concept at all, or just a habit of a brain evolved to navigate the middle world between atoms and stars. Particles don't wait in silence for us to discover them. They emerge when we ask. They flash into being when we insist on knowing. And then they vanish. And we're not outside that mystery. We are that mystery, asking about itself. You've made it this far, across the trembling scaffold of uncertainty, through the collapsing echoes of superpositions, past the tangled threads of entanglement, into the hollow roar of the vacuum, and back again. You've watched particles slip through walls, vanish into fields, and rise out of nothingness like sparks from a fire that never needed fuel. And now you stand here, not at the edge of understanding, but at its center, a place